material that you see in OChem 1. So what we're going to be doing now is we're going to jump into the chapter of alcohols, right? Now, the chapter on alcohols is a really, really long chapter. There are many, many reactions in here. So we're going to go over talking about alcohols. We're going to look very quickly at nomenclature. And then you're going to get, an amount of chemical reactions that will probably make you vomit. All right, so be prepared. And, like I said before, at this point, this is where we start to see overlap, significant overlap in some of the chemical reactions we've seen before. Right, so in OChem 1, there are reactions of alkenes and alkynes that generate alcohols. So there are going to be starting to be overlap. So some of it's going to be stuff that you've seen before, some of it's not. All right, and so sometimes that's a good thing. So we'll start by, go ahead and giving ourselves a heading: alcohols. And so in case you haven't memorized all the functional groups, these are going to be the hydroxyl groups attached to a carbon, right? And so if you go back to the origins of the word, it's actually Arabic, right? And that stands for the essence of water. And the reason for that is because, the history of chemistry by and large, and if you know a little bit about the human condition, it makes sense that history by and large in regards to chemistry goes way back to our ability to generate fermented drinks, beer and wine. And that didn't happen in Europe, right? Like the oldest literature you might go back to, purely literature, is Germany and France. But way before then, the cradle of life, which is kind of the area of the Middle East, we knew how to make wine. We knew how to make rudimentary beers. And so the term alcohol is actually Arabic for the essence of wine. Now, my favorite compound on the planet, of course, you've heard me say this many times, is the 2-carbon containing 1 ethanol. And this is something that you should all be familiar with. Not that I'm asking you to go drink ethanol. I'm saying you should know that it is the principal constituent of alcoholic beverages. So it's literally everywhere when you go to the store. The other one, especially coming out of COVID not too long ago, we were deficient in this one, which is isopropyl. It's rubbing alcohol. So both of these are very common. These are things that we can get at the store relatively easy. So the impact of this functional group and thus the chemistry that gives us these types of groups, and of course the nomenclature is really important. All right. Now, one of the things that I think is worth mentioning is looking at the structure. And I can say that it is very similar to water. Now, if you took organic chemistry with me, there's a section in the notes where we look at the case for water. And the reason for that is we're going into that because of the chapter right after we make the case for water in OChem 1 is the chapter on acids and bases. But one of the things that we talk about in OChem 1 is the fact that water can hydrogen bond with itself. And the same thing is true for alcohols, which is why, for example, when we started looking at alcohols, we talk about the fermentation process and the distillation process. And so we talk about water and alcohol as an example of organic molecules that are polar, because water is not organic. They can form 4 hydrogen bonds, but alcohols are, and they can form 2 hydrogen bonds. Oxygen can form hydrogen bonds, actually 3 hydrogen bonds. So it's structurally very similar. So if we look at just the functional group in general, we have an sp3 hybridized oxygen. And then of course, structurally we can look at water, which has a bond angle of 104.9 degrees, whereas something like methanol has a bond angle of 108.9. All right, so structurally very similar to water, capable of engaging hydrogen bonds just like water. It can hydrogen bond with itself. It can hydrogen bond with other hydrogen bond donors and other hydrogen bond acceptors, and then it can also hydrogen bond with water. Now, there's some verbiage that I think that we've talked about very briefly in OChem 1, so I'm going to bring it up again, but it's not unlike what we've seen before. This business of using the terms primary, secondary, and tertiary also applies when we're looking at the structure of alcohol. So a primary alcohol will basically be the hydroxyl functional group, OH. If that is attached to a carbon, only one carbon, being this one here in that case, then it's a primary. So the hydroxyl group is attached to only one carbon, and that carbon is only attached to one other carbon, then yeah, we can call it primary. So it's not unlike what we saw for what we call primary carbons and secondary carbons. We're just now extending that nomenclature to the alcohol functional group in general. And so in this next one here, which is isopropanol, that carbon, that CH group, is then bonded to two other methyl groups. So the carbon that the hydroxyl group is bonded to two other carbons, and that's what makes it the secondary alcohol. All right, and then the last possibility, of course, is something like this. That's a terbutyl group. This molecule is terbutanol. That carbon that the hydroxyl group is attached to is bonded to three other carbons, right? So then the fourth bond, carbon only being about 4, is the hydroxyl group. So this represents the extent of this usage. This is the tertiary alcohol. And so we're going to be using these terms quite extensively in this chapter, because there's going to be specific chemical reactions that can generate primary alcohols, certain reactions that can generate secondary alcohols, certain reactions that can generate tertiary alcohols. And we're going to introduce some really interesting chemistry that was Nobel Prize winning chemistry that allows us to target the synthesis of each of these. Right? So we will be using these terms extensively. And then finally, the other type of alcohol that we might run into that we've seen in the exam too are going to be the aromatic alcohols, and these are going to be the phenols. Right? Which the hydroxyl group is, for all practical purposes, a secondary carbon, but it's an aromatic ring, so we don't consider this a secondary alcohol. We'll just say it's an aromatic alcohol. Now, in the next page, after you finish writing this down, we're going to start talking about nomenclature. And as we start to get many functional groups under our belts, the nomenclature rules, if you remember, has to do with priorities of different functional groups. So coming out of OChem 1, we've got alkenes, we have alkanes, we have alkynes, and then we have the alkyl halides, right? Coming into OChem 2, we already saw we have aromatic systems that we've started to learn. Now we're going to have alcohols. And then right after this chapter, we're going to start getting into carbonyl groups. That opens up the door for carboxylic acids, carboxylic acid derivatives, aldehydes, and ketones. And so there's going to be so many different functional groups we're going to be exposed to. We're going to have to remember what the priority is for each of those functional groups whenever you're dealing with molecules that have multiple functional groups in the structure. And so the only time that I ever provide you a list of the functional group hierarchy is in this chapter and on the next page. So the reason I'm telling you that, because once we get to it, I'm going to say, dog ear that bit of your notes, or put a little flag on it, or whatever, so that you can come back to that in your lecture, spiral, whatever it is you're taking your notes. Because you're going to have to make reference to that as we go further on in the material. Right? Because I'm not going to give it to you again. It's just, it's just too much for me to continue to remind you. Hey, here are the priorities. Hey, here are the priorities. Hey, I'm just going to do it once. It's going to happen in this chapter. Does anybody still leave this up? All right, so nomenclature. And I don't think the nomenclature is going to be fairly difficult. This is not the part of this chapter that I think people by and large struggle with. It's the immense chemical reactions that you're going to have to go through. Fair warning. All right. So for the most part, we call them alkanols. And what that means is, if you know what kind of alkane chain is attached to the hydroxyl group, then you pretty much add an OL after that, and then you got your name. So, of course, the suffix is what's changing. So we lose the NE, well, actually the E, and replace that with OL. Right? So, very briefly, we can jot the rules as, the first thing we're going to do is we're going to find the longest chain. And in the absence of other functional groups, of course, this group is going to say there's only a functional group, it's alcohol group. the longest chain has to have the carbon that has hydroxyl group on it. Of course, all that goes out the window once we start putting on higher priority functional groups, which isn't going to happen until we get to the next chapter. Once you figure that out, we're going to name it from the side closer to the hydroxyl group. Right? So that's also an indicator that, hey, we're going to be numbering this thing, we're going to be numbering it with the carbon 1 being the carbon that's directly attached to the alcohol. And then we'll go from there. And then once you've done that, then we have to deal with any attached substituents. So let's take a look at an example. How many carbons is the longest chain on this example? 5. Are we going to number this left to right or right to left? Right to left. Yeah. This is going to be carbon 1 right here. Right, so it's carbon directly attached to hydroxyl groups. 2, 3, 4. And then at 4, of course, that's a terbutyl group, so it doesn't matter if you go up, down, left, it's the same thing. I'm just going to go straight through. Right? Either way, if you go up or down, you're going to have a 4,4 dimethyl situated there. And so then, the only other functional groups attached to that 5-carbon chain are the 3 other methyls. There's a methyl group in carbon 2, 2 methyls in carbon 4. So then this should be a 2, 4, 4 trimethyl. And then here we'll do 1 pentanol. Let me remind you that that is not an aromatic group. We're still stuck in the previous chapter. So following the rules, if you're looking at this disubstituted cyclohexane ring, right? This gets carbon 1. There's a plane of symmetry with regards to the numbers, right? If we go clockwise or counterclockwise, it doesn't matter. You still get bromo at 4 position. All right? And you can see from the structure there's stereochemical information provided. So there's also going to be a stereochemistry name that we're going to have to append at the beginning. So what term would we throw in to describe the stereochemical relationship between the hydroxyl and the bromine group? What is that? Trans. Yeah, that's trans. So we can start out by saying this is trans, this is popping forward, this is popping backwards, 4 bromo, and then this would be cyclohexanol. Let me show you one that I like to usually put on the exam. I'm not saying I'm going to put this example on the exam, I'm going to put something like it in the exam because it introduces something interesting. And what it introduces is we have to account for the fact that there's an alkene present and we need to indicate what number that alkene is present. The alkene is not necessarily a substantial that you you would normally deal with in terms of like, oh, it's a 4-bromo or a 2-methyl. It's not quite like that. It's a little bit different. So first off, we have a stereochemistry to contend with, right? Bond rotation around a double bond is forbidden, and so we know double bonds can either be like this, or they can be like that. We can describe them as being cis and trans, but let's say for this case, if we're not dealing with cis and trans, I'm asking you whether or not this is an E versus Z stereo configuration here. So which one is it? Do you remember that? Is it this is an E or is this a Z? It's an E. Yeah. You remember this would be Z because the two groups are on the same side. So if the two groups are on the same side, this would be E. So Z same side, the other one would be E. The groups coming off the double bond are not on the same side, so they're an E. So we can start out this nomenclature by calling this the E, which in this case would be analogous to the trans. All right. Now the numbering doesn't change. We still number with the carbon, starting the hydroxyl group as carbon 1. And so here what we need to do is we're going to let the people know that there's a double bond at carbon 2. And because there's 5 carbons, what's the prefix going to be for 5 carbons? Pent, right? But because there's an alkene here, just like what we've seen before, it's usually pentene. But because it's an alcohol, we're not going to put pentene, we're going to put pentin. And then we introduce the letter, the number, to let them know what carbon the alcohol comes off. And the reason for that, sometimes there's not always going to be the alcohol carbon, there's special circumstances, not always the case. But for these ones where you have a double bond or even a triple bond somewhere in the chain, it would either be like a 2-pentin, if it was a triple bond, it would be a 2-pentyne without the E, and then of course you would append the OL towards the end. Right, so this one's a little bit of a difference. Right. So let me write down kind of for your notes and say that if you have an alcohol, if an alcohol has a carbon-carbon double bond present or a carbon-carbon triple bond present, then the suffix OL, ol, goes behind the name, but still has priority. Right, so the fact that the OLs at the back is an indicator like, okay, the functional group there, but alcohol takes priority over the alkene. Which I think is a good time to list in order of priority the functional groups that you will encounter in organic chemistry. Now, this is not exactly an exhaustive list because there's a whole bunch of groups that are just, uncommon. So for example, there's things called imines, there's azides, and all these other groups. Like those are not something you're going to encounter usually in a class like this. So I'm not going to give you the exhaustive version of this, but I'm going to give you all the functional groups that I'm going to require you to memorize. So in organic chemistry with me, there's like 16 I require you to memorize, or 16 I require you to memorize. Here it's the same 16. One of the things I like to do at the end of exams, usually on the final, is I like to show you what you've learned by saying, hey, do you know all the functional groups? Because then when you go take Dr. Larkin for Biochemistry 1, like he's going to expect to know those functional groups. Then he talks to me, we chat, and he tells me, oh yeah, this dude doesn't know those functional groups. Then it's like, oh, that's fun because I taught them and it was on the final. So, something to commit to memory. Carboxylic acid, of all the functional groups, has the highest priority. Right? What that means is you can have all the other functional groups on this list present on the molecular structure. If there's a carboxylic acid present in the nomenclature, it is considered a carboxylic acid as the base name. Right? The next one under that are going to be the esters, which are a carboxylic acid derivative, followed by the aldehydes, followed by ketones, followed by the alcohols, followed by the amines, followed by alkenes, followed by alkynes, alkanes, ethers, and halides. Now, why exactly is this the case? I have absolutely no idea. It comes back to the International Union of Clear and Applied Chemistry. IUPAC made these designations. When I look at these functional groups, I'm like, what did ether do to make everybody so upset? Because if you look at this nomenclature, everything that has the oxygen atoms are well above it, right? It's alcohols, ketones, aldehydes, esters, all those have oxygens. Then you get to nitrogen, then you get no heteroatoms, and then there's ether, which is carbon, oxygen, carbon, and then halogens. Right? So I don't know why. I personally like ethers. They're really nice solvents. Sometimes they smell nice. They catch fire very easily. You know, I used to have a buddy who worked in a biology lab, and they used some sort of ether to knock out the mouse before they did horrible things to it. It's a great solvent. Not that research was horrible. I don't even want to tell you what they did to that mouse. It was horrible. Like, I sat there and watched it. I was like, dude, how do you do this? This is horrible. You're a horrible person to do that. Anybody still need this up? All right, so here's an example. Now, of course, this is an example that includes a functional group that we haven't quite covered yet, right? That there's a ketone in this molecule. If you look at the priorities, you can see that the ketone is higher priority than the alcohol, which means that whenever we decide which carbon gets the 1, because the ketone takes priority, this becomes carbon 1. And again, it doesn't matter if you go clockwise and counterclockwise. In this particular example, you still have the alcohol group at carbon 4, which means since the alcohol is not the base name, we need to figure out what that functional group is as a substituent. And the alcohol as a substituent is a hydroxy. So for something like this is 4-hydroxy cyclohexanone. And then we'll learn later that ONE, that suffix O, is the indicator that the base name is a ketone. All right, here's another molecule, 3 carbons on this one. Now it has basically the king, carboxylic acid. Right, so this is going to be some sort of carboxylic acid with a hydroxy group, but it's the same situation, right? That means that the carbonyl of the carboxylic acid gets carbon 1. We're going right to left, there's a hydroxy group in carbon 2. Then something like this will be called 2-hydroxy. And then it's 3, so it's propanoic acid. And again, when we get to the chapter of carboxylic acids, before we get to the semester, the oic acid is the base name to indicate carboxylic acid. Just like we saw for some of the aromatic compounds, and this is true for other organics as well, there are such things as common names, right? Just like we saw that for methylbenzene, that common name is toluene, right? I said that if you go to Home Depot or Lowe's and ask for methylbenzene, they're probably not going to know what you're talking about. Ask for toluene, and oh yeah, know exactly what it is. It's in the paint section, right? And so when we look at the single carbon containing alcohol, the IUPAC name we know, this is methanol. But people who are not skilled in the art might know that this is methyl alcohol. We should know both, right? This would be ethanol, but this is also known as ethyl alcohol. Here we have a terbutyl group, so it should be terbutanol. We can abbreviate as T-butyl alcohol. If, for example, you're looking at a molecule that contains two hydroxy groups, it is not uncommon to see the use of the term diol, and by relationship, triol, indicating, of course, how many hydroxy groups are present. So, something like this example of that. So here we have a cyclohexane ring. We got hydroxy groups at positions 1 and 3. What's the stereochemical identifier for this? Is this a cis or a trans? Trans. Okay. The bold bond is popping towards us, the hatch bond is popping away. So we can start the name of this one by saying it's trans. And then in this case, no matter where you start, from either the one pointing towards us or one pointing away, it's still going to be a 1,3. So this will be 1,3 cyclobutane diol. We have a di-substituted cyclohexane ring. We've got hydroxyl groups at 1 and 2 positions. They're both pointing out of the plane of the screen towards us. So this is not a situation of trans, this is cis. And this would be 1, 2 cyclohexane. This one in. Usually, if people are taking organic chemistry 2 in the fall semester, just remind people of Christmas or Santa Claus. We have a molecule like this. Applying the symmetry right down the middle. So it doesn't matter if you number left to right or right to left. You're still going to have hydroxyl groups of carbons 2, 4, and 6. So just for good measure, I'm just going to do the numbering like this. So this is 2, 4, 6. 7 is heptane. And because there's 3, it's heptane triol. Everybody still read this up? All right, so let's have a look at the properties. Now, one of the things that we can start to look at is comparing the molecular structure of alcohols and their physical properties to other known organic compounds. So this right here is propane. Now, in terms of molecular dipole moment, right? Remember, molecular dipole moment is the vector for polar covalent bonds. Since there's no heteroatoms in something like propane, then there's no polar covalent bonds. If there's no polar covalent bonds, then there's really no part of this molecule that's pooling a tremendous amount of electron density that would create a vector that we can measure in its polarity. And so this is 0.08 Debye. The boiling point of this is negative 42 degrees Celsius. Now, room temperature is 25 degrees Celsius. It's probably a little bit colder in here. This is probably like 23. But what it means is that this thing right here we know is a gas at room temperature. Right. Now, if you replace the central CH2 group with an oxygen, then this is dimethyl ether. So now we have a heteroatom. We have two polar covalent bonds where we know that oxygen is withdrawing electron density. Right, so you have two polar bonds like that, which means you've got a vector straight up the middle pointing upwards towards the oxygen to generate a molecular dipole. The molecular dipole for this is 1.30 Debye, and its boiling point is negative 25 degrees Celsius. So it's still a gas at room temperature, but not to the extent that propane is a gas at room temperature, which has a boiling point of negative 42. Now, if we simply change the structure, and rather than having the OCH3 bond, we have the O hydrogen bond there. Well, that changes the game substantially. The molecular dipole for ethanol is 1.69 Debye, but now it has the ability to form hydrogen bonds. 3 of them. 2 to the oxygen, with the oxygen as a hydrogen bonding donor, and 1 as a hydrogen bonding acceptor with the hydrogen. And they can engage in those hydrogen bonds with itself. So for absolute ethanol, the boiling point for that is now 78 degrees Celsius, which is quite hot. To give you an idea of how hot that is, if you spent the summer here in Corpus Christi, you know that the hottest it gets. Right? You know what that feels like. That's usually in the high 30s. Heat index might be in the 40s. And that's a humidity sort of effect. But at 78 degrees Celsius, yeah, like, you probably tell. So it's not 100, but you don't want to put your finger in it. The other thing that's interesting about these alcohols is now we see that they're amphiphilic. And as we increase the extent of the hydrocarbon portion of the molecule, that alkyl chain, we increase the amphiphilicity, because this hydrocarbon portion is hydrophobic, And then, of course, this component here is hydrophilic. It's hydrophilic again because that's a polar covalent bond that can form hydrogen bonds with water. Once that chain starts to get so long, we discussed this a little bit in NoChem 1, then you start to have amphiphils that can self-assemble in solution. You know, the foundation for molecules that become surface active. And they can decrease the surface tension of water, and they'll behave like soaps and detergents. Now, it turns out that for alcohols that have 4 carbons and larger, the hydrophobic component wins. So I'll put here that the hydrophobicity wins, which means that they are typically poorly soluble in H2O. You can usually heat them in, but as I mentioned before, as it starts to cool down, these molecules will self-assemble. And sometimes they'll form micelles, but if they're sufficiently insoluble, the likelihood is because they've self-assembled and the aggregate structure has such a high molecular weight that it just precipitates out of solution. And then at room temperature, maybe it's just outside. For methanol all the way to propanol, these ones are all soluble in water. And thankfully so. Ethanol needs to be soluble in water for us to make wine and beer. Now, this is a discussion about solubility. That's not necessarily a discussion about what their natural state is at room temperature. If you're looking at methanol all the way to C12, these alcohols are liquids at room temperature. If you're looking at alcohols greater than C12, then these are going to be solids. You weigh them out on a scale and use them in their reagents. I will say that, for the most part, all alcohols have what can be characterized as a light, pleasant smell. Now, of course, it's a very subjective statement. But I will say this, that it doesn't smell like fart, right? It's not a thiol-containing molecule, which is one atom different. You change that oxygen to a sulfur, and now you've got the smell of skunk or something similar. Right? So by comparison, it is a fairly pleasant smell. Now this can become an issue. Later on in the chapter we'll talk about this, but you know, it means that if you spill some of this on the floor, animals will readily go lick this up, and so will children, because it doesn't smell bad. You know? So you gotta be very careful. And we'll talk about that a little bit later, what that does and why it's bad. Drink certain alcohols. Of course, all of them to excesses is bad for you. I think it goes without saying that as a functional group, there's quite a lot of commercial use for alcohols. The first one we'll look at is methanol, which is also known as wood alcohol. Now, the reason that it's known as wood alcohol is because if you subject wood, for example, to the fermentation process of the cellulose of wood, you don't produce ethanol, you produce methanol. Which means it's actually quite cheap to make, right? Consider what you have to ferment to get ethanol, which would be drinking alcohol, a whole bunch of things, but, it's not like wood. Wood is pretty dense. But the problem with methanol is, I tell you, you come across a bottle, please don't drink it. Drinking it will cause blindness. And you don't need much of it. Apparently, of course this is dependent on the person, the natural body weight as well. 15 milliliters is all it takes to get you to go blind. It's not allowed. This can kill you very fast. It can cause death at 15 milliliters or greater. The use of methanol to drink is something that you'll see in the news every now and then, coming out of third world countries, particularly India. Not that I'm picking on the country, but it's true. You can Google this. Right? Sometimes a company or somebody who's selling alcoholic beverages is trying to save a buck and will instead sell methanol. Or if the fermentation process is done incorrectly and the distillation process incorrectly, there might be a high concentration of methanol in an ethanol sample. As we look in the news, you Google methanol poisoning at a party, you'll find there are numerous parties and weddings where everybody got killed because they bought these little pouches of alcohol. They thought, oh, these are, we're going to party. It wasn't ethanol, it was methanol. It kills you very fast. When I was an undergrad, I spent the summer at the California Institute of Technology, Pasadena, California. A really, really famous university. They run the Jet Propulsion Laboratory and stuff. Just outside there in Pasadena on Colorado Street was a bar called Amigos, which was a cantina. And it was really famous because a lot of Nobel Prize physicists and chemists would go there because it's literally 2 blocks away from the university. So of course, have libations. So of course I took it upon myself to go there, and they're known for their margaritas. And being from South Texas, Hispanic, I said, hey, I like margaritas. And I noticed in drinking their margaritas that my vision started to get slightly blurry. And it was then that I thought, I wonder if there's methanol in tequila. I didn't know. There is methanol in tequila. If you look at any bottle of tequila, there is an acceptable amount by the FDA. I think the FDA regulates alcohol, maybe it's something else. There's an acceptable amount of tequila, which is, agave fermentation, in the bottle. So please be careful when you drink that. They are required to indicate the percentage of methanol in your tequila. And so whenever people tell you that they don't, tequila just doesn't work well with them, it could be a variety of different compounds that are the side products of fermentation of agave, but it's also a little bit of that blurry vision because there's methanol in it. So don't drink too much tequila, all right? Because, you can see what it does. Now, the process, there's other processes by which we can generate methanol. So it's not just the fermentation of wood. You can take carbon dioxide, 2 molar equivalents of hydrogen gas in an industrial process that requires these materials to be heated to about 300 to 400 degrees Celsius, very hot, in the presence of some proprietary catalysts that if they told us it would kill us, to produce methanol on an industrial scale. And then lo and behold, you remove carbon dioxide from the atmosphere and you don't grow trees. Yeah. Yeah, I'm not sure, but probably so. And it's also because if you look at the distillation process, which we'll discuss in a little bit, the high boiling azeotrope that gets formed with the different alcohols in water, it becomes really difficult to separate. So, it might be. Yeah. But it's there. You can check it. I was shocked. I was like, what? Surely there's no methanol in this. Yeah, every bottle I looked at, there is methanol in there, like trace amounts. Some more than others, I guess. All right, so methanol, of course, we talked about it being abused and things like this, and of course, but it is rather a common solvent. It is a common organic solvent. In my own research lab, for example, we have squirt bottles of it, right? And we use it to clean glassware because it's this right polarity between, just water and organic component. It dissolves a lot of things nicely. So it's a very, very common organic solvent. It is a very common chemical feedstock. So I'm not sure, I think some of you ran, the ether synthesis, but you can use methanol, for example, to generate esters. You can use it to make methanoic acid. You can generate all kinds of different carboxylic acid derivatives. So it is a common chemical feedstock, and it's also used in combustion. So used as fuel in some cases, right? Because it is a flammable solvent. So yes, it's definitely that. All right, ethanol, also known as grain alcohol, although we know grain is not the only thing that you can ferment to get ethanol. It's obtained by fermentation. So there's such thing as rice wine. You can ferment rice, you can ferment grapes, you can ferment rye. In China, the world, the number one consumed alcohol on the planet is the fermentation byproduct of using sorghum, and it's known as baijiu. And the only reason that it's the most highly consumed alcohol on the planet is because it's the one that's most consumed in China, whose sheer population is like over 1 billion people. So it blows whiskey and tequila out of the water. The stuff is disgusting. I read an article, I can't remember if it was peer-reviewed literature or not, but the conclusion was that you had to drink this stuff 75 times in order to begin to acquire a taste. I can tell you from personal experience, having lived there for 5 years, the consumption of baijiu is required in order to climb the social ladder both amongst your peers and amongst your colleagues. So, for example, business dinners, they will give you a small little picture of it, and then they give you this little thimble type shot glass because you can only sip it in small amounts. And when you open up this bottle, it smells like gasoline. The bottle that everybody likes to buy is $400, and it's a white bottle. I forget the name, but anyway, that's fermented sorghum, and it's just, it's kind of gross. But anyway, so it's not just grain alcohol. There's all kinds of things. But the fermentation process is pretty well known. Right? The idea is that if you've got some sort of sugar, then you can produce 2 molar equivalents of alcohol plus 2 molar equivalents of carbon dioxide. The fermentation process typically produces about 40 to 50% ethanol in the solution that is undergoing fermentation. And then, of course, people want to have a good time, and so, and this is hundreds of years worth of chemical experience, we learned that you can distill out, of course, the alcohol to obtain 96% ethanol, which is the most pure you can get via distillation. The reason for that is because water and ethanol have what is known as a high boiling azeotrope, which means when you have water present, because of the hydrogen bonds that exist between water and alcohol, when you start to boil that mixture in the gas phase that you're condensing on the other side of the still, the highest amount you can get is 96%. So if somebody comes up to you and says, hey, this is pure alcohol, it's moonshine, it's not pure, it's 96% at best. And that's assuming that their distillation apparatus was 100% efficient, which none of them are. Right? And then companies usually multiple distill to even reach that. Now you can get pure ethanol by taking something like this, and you can subject it to dehydration to get 100%, which is absolute ethanol. Right? So you can do dehydration. There's a couple of ways that you can do that. You can do it chemically. So you can put something in there that will consume and react with water to remove it. There's materials known as molecular sieves, which are porous materials. And the pores of these molecular sieves are activated in an oven, and the pore size of these materials is exactly the same size as water molecules. When you drop them in there, they will just adsorb water into them, and then you can generate absolute alcohol. Now, I want to make the point, because you guys are no longer laymen. When you go to a liquor store and you see the brand Absolute Vodka or something like that, that's not 100% ethanol. right? It's pretty high up there, but it's not 100%. If people were selling 100% ethanol, people would be killing themselves all the time, right? That 4% water that's in the moonshine, like you can't really take too much of it anyway, because again, it'll kill you in the blind. That's kind of keeping you alive, right? 100% pure ethanol. You might see it in the teaching labs, but it's usually denatured, so they usually put stuff in there so you don't drink it. But, it is true that if you had 100% ethanol and you went and diluted it with water, then you got vodka. That's just, so don't do that. And the likelihood is high that if you do see something like that in the lab, it's been denatured. So don't try to consume it or steal it and then consume it. You'll be sorry. But you should know these things because it's part of the education process. You can take ethylene gas in the presence of water, and in an industrial process it involves pressurizing the vessel to about 300 atmospheres at 300 degrees Celsius, and again, in the proprietary catalyst, which will kill us if we knew it, you can make pure ethanol. It goes without saying that ethanol is also a very important solvent for chemical reactions. It's a very important chemical feedstock, just like methanol, both in industry and, of course, academics. And then the other one, which I think is worth spending just a little bit of time talking about, is isopropanol. We know this is rubbing alcohol. If you take propene, presence of water, same process, 300 atmospheres, 300 degrees Celsius, proprietary catalyst, and we can produce ethanol on industrial scale. And of course, I think it goes without saying, like, what exactly the uses of ethanol are. It's rubbing alcohol. I like to use it, dilute it down, use it for cleaning. I've got so many kids. Alcohol works really well. The paint on the walls, we decided to get something that we can use to paint the walls with, like, marker and crayons. So my go-to is to use ethanol before I would switch to acetone or something crazy. You probably remember it from COVID. We use it to kill microorganisms, and there was a huge lack of the stuff once that thing sort of hit, in academics. Universities were the only places that pretty much had a lot of it. Everybody else couldn't find it at the stores, and then people started hogging it. Remember that? Remember people had like cases of rubbing alcohol? It was a weird time. I think there was like fires at people's houses because he stored them in ways. I don't know. So it goes without saying that, isopropanol, methanol, ethanol are just three alcohols to name, so many more that have a very, very important commercial uses. And the chapter of acids and bases in the textbook, we talk about the acidity of alcohols quite a bit. We use them as principal examples of, when we get to start talking about Lewis acid, we find that a molecule that has a heteroatom, thus non-bonding electrons, can act as a base. Alcohols can behave as both. So a base can react with an alcohol to deprotonate it. So for this chapter, we're mainly concerned with it behaving as an acid. So let's say you had some sort of base. I'm not going to provide an identity to this base, maybe it's hydroxide. So in this case, B is not boron, it's B for base. Lone pair, negative charge. So it's very nucleophilic and very basic. And so if you remember from, OChem 1, the attack comes from the base to the acidic proton. The electrons that are holding onto that hydrogen donate back to the heteroatom. This is a process that's in thermodynamic equilibrium, that if the base is strong enough, you can generate the deprotonated alcohol, which is known as an alkoxide. And the alkoxide is a term that is a generic term for an alcohol that's been deprotonated, whose identity you don't know. If the alcohol was methanol, the deprotonated form of methanol would be methoxide. If it was ethanol, it would be ethoxide. If it was isopropanol, it would be isopropoxide. If it was terbutanol, it would be terbutoxide, right? Just like we have alkyl groups, which are an umbrella term for all kinds of hydrocarbons, but we can specify what those alkyl groups are by saying whether or not they're methyl, ethyl, propyl. The same is true here. So the alkoxide anion is the deprotonated alcohol that results of that interaction. Now, of course, because these acid-base reactions are in thermodynamic equilibrium, the extent of these reactions is highly dependent on the strength of the base in relation to the pKa of the alcohol. So, for example, when it comes to water, I want to point your attention to the fact that the equilibrium arrows are now about equal in length, whereas in the previous example on top, the equilibrium arrow is showing that the reaction lies heavily in favor of the products. That means that if we were to calculate the Ka for this process, you'd find roughly 50-50 of alkoxide versus alcohol versus water versus hydroxide. So again, this is kind of a short review of acids and bases. Alright, so if you remember, the way that we discuss acidity is about the pKa. The lower the pKa, the more acidic. So what we're going to do is look at a series of alcohols, and I'm going to list for you the pKa's. Now don't worry, I'm never going to examine you on this. I'm not going to ask you what's the pKa of this alcohol. That'd be ridiculous. But I want to show you the trend that emerges if you go from something like methanol, increase the hydrocarbon length to ethanol. This right here would be isopropanol. Compare that to the pKa in water, which is 15.7. Acetic acid, which is vinegar. Of course, hydrochloric acid, which is negative 2.2. So you can see that, as we start to increase the hydrocarbon chain of the alcohol, we see an increase in the pKa. Right? So methanol is at 15.5. So the pKa of methanol is very, very close to the pKa water. And we're going from 15.5 to 18 with isopropanol. Of course, we know kind of the acidity of vinegar because, you probably tasted vinegar eating a pickle. You know that that's tart to the flavor, that's at 4.8. Right? And so what this means is, depending on the alcohol and the conjugate acid of the base you use, that's really going to determine whether or not the base you use is strong enough to steal the proton from the alcohol. And so this right here is an example of that, right? Because Water in and of itself can behave as a base, but it's not a strong enough base to pull off the proton, which is why that equilibrium is such. You'd have to look at the hydroxide anion to figure out whether or not, the pK of its conjugate acid, which is water, right, 15.7, is sufficient enough to deprotonate something like methanol. It might not, right? So one of the things that we can show you that doesn't necessarily involve a base, but can deprotonate alcohols is the use of alkali metals. And so if you take something like an alcohol and chuck in elemental sodium, you will deprotonate that alcohol. And so you'll generate the alkoxide and you'll trap it as the sodium salt. And so this is known as sodium alkoxide. And in the process, this will liberate half molar equivalent of hydrogen gas. And this sodium alkoxide is going to be something that we're going to see later as a really, really basic reagent. And also as a really strong nucleophile. We can use sodium alkoxide, for example, to generate esters. We can use sodium alkoxide to generate ethers. A really common reagent which is commercially available is taking tert-butanol, this is how they make that reagent, and exposing it to elemental potassium. That has the effect of deprotonating the tert-butyl alcohol group, and you can trap it in solution as the potassium salt. And so this would be potassium tert-butoxide. And that's commercially available. You can actually buy that. Now, of the alcohols, and shifting gears here, the aromatic alcohols in which the hydroxyl group is directly attached to the aromatic ring, these ones are the most acidic. I write that here, phenols are more acidic. And the reason for that is because the minute you deprotonate that, let's say, for example, you chuck elemental sodium at it to generate the sodium phenoxide anion. So we can draw the sodium phenoxide anion very easily. All it is just O minus upstairs with 3 lone pairs of non-bonding electrons. This is now resonance stabilized. So we can draw the resonance structure where one of these lone pairs kicks down. To avoid the Texas carbon, one of these pi bonds breaks, it donates electrons to the nearest adjacent carbon. So now we have a carbonyl, which has been formed upstairs. We have a lone pair of non-bonding electrons on the carbon upstairs to the right. That can then reform to make a double bond that donates down to the adjacent carbon. We can draw that again. We can do it one more time too. That's going to make a double bond, that'll go there. And then of course we do it again. And it comes full circle. And so these resonance stabilized anions are really important, right? That's going back to what Chem 1, right? We said that, in an acid-base reaction, there's a couple of things to consider that determines the strength of the acid. And that is, what is the acid's conjugate base and how stable is it? If the conjugate base is unstable and it's highly reactive, such as the case for methoxide anions or potassium tert-butoxide, which is why those are very, very, very important reagents. You can do all kinds of chemistry with those. But something like this, it's not as reactive. it's more stable, persistent solution, because it's distributing that negative charge across 4 different atoms. And so as a result, that proton is a little bit easier to convince to pull off. You don't need as strong a base to pull it off, and so that translates to it being more acidic. All right, so at this point, we're going to talk about preparative methods of alcohols, right? So the organic reactions, this is where we're going to see some of the overlap of stuff that you've learned or seen before. We're going to learn how to make alcohols, talk about all the ways we can make them. And then once we make them, there's a whole list of chemical reactions that we can do with them once we have them, right? So that's one of the reasons why this particular chapter is so long, because there's a lot of ways to make alcohols, and then there's a lot of reactions that you can use to convert them to do other things. Does anybody still need this up? All right, so let's discuss preparative methods. And so as I pointed out, we saw some of these before. This is going to be either the SN2 reaction or the SN1. So this is from OChem 1, of course. One of those reactions involved the substitution of alkyl halides. If you remember, with regard to the SN2 reactions, the alkyl halides were important because they polarize that carbon, and because that carbon is losing electron density to the halogen in this polar covalent bond, which I've highlighted there, that is an electrophilic carbon, right? And electrophilic basically means that anything in there that has a lot of electron density can then swoop in. Usually it's some sort of anionic base, and it, if you remember, approaches with backside attack, and there's stereochemical repercussions to that. The backside attack triggers there's a chiral center, for example, inversion of stereochemistry. So that was an R enantiomer becomes an S, that was an S enantiomer becomes an R. And as written, you generate the alcohol, you have a halide floating around, and we remember that this is a reaction that competes with elimination. And the nature of that competition is dependent on how sterically bulky the base is and how sterically bulky the substrate of the alcohol is, right? So all that is end of OChem level material. That material, of course, is always in the textbook. It's in the old notes for those who had me, probably in the old notes if you had Dr. Silver. It's definitely in the textbook, so I would go there. It is not going to be in the list of reactions from antiquity. So that kind of nuanced chemistry and the rules behind it, you'll have to go back and review. All right, but the reason I bring this up is because there's a whole host of reactions we learned last semester, right? So one of the first reactions that we learned in the chapter of alkenes was the acid catalyzed addition of H2O, right? It was a hydration reaction. And all that was that if you have a carbon-carbon double bond, then all you needed to do was to have a hydrogen source in the presence of water, right? Which is the same thing as saying H3O plus. So you'll see that on my exams usually, for those who haven't taken it before. H3O plus is hydronium. Whenever you have an acid in water, the H plus isn't just floating around, it's already been attacked by water. So H3O plus is the same thing as writing H plus over water. And if you remember, that breaks the carbon-carbon pi bond. It attaches a hydrogen to the least substituted carbon, which in this example, you can't tell because it's equally substituted. But basically what I'm saying is that this type of substitution follows Markovnikov in geochemistry. So you have to remember Markovnikov's rule is in effect for this transformation. And you have to remember that rearrangements are possible because for this transformation, it proceeds through a carbocation intermediate. Right? And so, if you remember, carbocation stability is that the tertiary carbocations are more stable than the second, more stable than the primary, And so rearrangements can occur via 1,2 hydride shifts or 1,2 alkyl shifts. The examples that we use in OChem 1, because we introduce it to you first and foremost in OChem 1, is a 1,2 methyl shift. But the truth is, it can be a 1,2 alkyl shift. So it means an isopropyl group can pop over, or an ethyl group can pop over. Now there's differing rearrangement rates depending on the group, but for this point, I want to say that alkyl shifts rather than methyl shifts is the way I want you to learn that, because it's not just methyls that can rearrange to put a carbocation in a more stable position. Right. We have a few minutes left, let's do one more. Maybe you remember this one, oxymercuration, demercuration. The dead giveaway for this one was that there's a reduction step that involves sodium borohydride. But the oxymercuration involved an organomercury reagent. Usually it's going to be some sort of mercury center, which is has 2 alkyl groups. So in this case, it's acetyl groups in the presence of water, and then you end up getting a mercurium ion that you have to reduce off using sodium borohydride, NaBH4. And that does the exact same thing as your acid catalyzed addition of H2. So, just the method. This also follows our common. So, these 2 reactions thus far are review for OChem 1. And with 3 minutes left, we can stop here, but there's many more to come. So we'll see you on Thursday. Get some more reaction in their mouths.